Hello, friends. All right, welcome to our first full lesson of calculus. This is called Introducing Calculus. Can change occur at an instant? I am super excited to walk through this calculus journey with you. And what I want you to really focus on as we go through this journey is the familiarity, okay? Today, we're going to introduce some concepts to you, but at the end of the day, there's nothing mathematically that I'm going to do with you right now that you didn't do in grade 10, okay? Today boils down to, do you know the slope formula? Sure, you know the slope formula, right? When you're calculating the slope, you go y2 minus y1 over x2 minus x1. You need 2 points to calculate the slope. Awesome. That's really all we're going to do today, okay? So you got this. First lesson of calculus, easy peasy lemon squeezy. Okay. The definition of a linear function way back in grade 10, I'm just going to hide my head for 1 sec there, was a function that had a constant rate of change. This meant that the rate always stayed the same, right? If my slope on a line was 2, that meant every time I was on the line, I could go up 2 over 1 and I'd be back on the line. I could go up 2 over 1. I could go up 4 over 2. That's still a constant rate of 2, okay? Most things in real life, however, are constantly changing. And so we find ourselves trying to find the rate of change for the moment. If I just took a snapshot of some dynamic thing happening in the world, what is going on, click, right at that moment, okay? That's called an instantaneous rate of change. I'll define that in a second, but that's essentially just the rate of change right at that second in time. The rate of change can also be represented as a line with a defined slope. And so we can represent the rate of change at any moment along a function by creating a tangent line at that moment. Okay. Now, just to make sure we're all on the same page, a tangent line is a line that will hit another function once and only once. Okay. Now, you smart people out there are thinking, okay, you just said I was going to use the slope formula. I need 2 points to get the slope formula, right? I need an x1, y1, and I need an x1, y1, and an x2, y2. The tangent line only has 1 point, so that presents the problem. How do we figure out the slope of a tangent line when a tangent line actually only has 1 point? Okay, and that's actually what we're going to discuss for the next little bit, the next few lessons. Okay, so just to dive in though, in the graph below, how does the rate of change differ between x equals -4 and x equals 2? So I'm just going to hide myself for 1 sec in case you don't have the book with you so that you can see that. So at x equals -4, let's just take a look at that one for a sec. At x equals -4, I am right there. So I'm thinking, okay, I want to draw some sort of a tangent line. I want to get some sort of a straight edge so that I can draw a line that kind of looks like that, okay? And that will hit my graph once and only once. So if I was to do that, I might get something that looks like that, okay? Now, one thing I want you to be super comfortable with, no matter what your picture looks like, you would want to tell me right now that that slope is positive. If we were going to estimate what that slope is according to my line, it looks like, what are we going to do here? 1, 2, 3, 1. It looks like it's about 3. Okay, so at x equals -4, the rate of change is close to a positive 3. Okay, now we're going to do the same thing at x equals 2. So here is my line at x equals 2. Okay, and what's the slope of that guy? Well, first of all, I want you to say it's negative. Okay, that should feel decently comfortable to you. And then we're going to go, okay, well, it looks like what? 1, 2, looks like -3 actually. Okay, so at x equals 2, the rate of change is close to -3. Point I want you to understand right now, as I go along this function, this green quadratic that you're looking at, the rate of change is constantly changing. Right? If I looked at, I just want to put my ink back on here. If I looked at the rate of change up here, which I'll actually get you to write down in a minute, that one looks like that. If I looked at the rate of change here, that might look like that, right? If I looked at the rate of change here, that one might look like, ooh, you're testing my ability to draw. Ooh, no, that's not a good one. Let's erase that one because That's actually a secant line. Okay. Have I introduced the word secant to you yet? Secant means you are going to touch twice. Okay. So if I was going to do a better job of that, oh, the pressure's on now. Okay. Something like that. Okay. I'm doing it freehand, so you got to give me a little grace. Okay. Perfect. Now, I'm just going to hide my head for a sec. And so the slope of a tangent line can be viewed as a rate of change. Since slope is the ratio of the change in y over the change in x, that is, slope is delta y over delta x, we say that slope is the rate of change of y with respect to x. So this whole conversation around with respect to, when we talk about that, the with respect to is on the bottom. Okay, that's something that, if you can remember, is going to help you as we go. Okay, so when we say the slope of y with respect to x, that means we're talking about y in terms of x. So that's why x is on the bottom there. Okay, so now we're going to walk through an investigation and we're going to look at changes in rates. I'm going to start with velocity. Okay, so here is my first little example. Suppose Sam drove to Edmonton, a distance of 300 kilometers in 3 hours. We can use the following formula to determine Sam's average velocity. So average velocity will be the change in distance divided by the change in time. Okay. Well, if I need the change in something, I need to pick 2 points and subtract them, and that'll give me the change. So that is the slope formula, right? If I'm looking for the change in distance, if distance is my y value, I subtract 2 y values, and then I subtract the corresponding time values, and then that's going to get me my speed or my velocity. Okay, so we say delta S over delta T. So this is my average velocity. Delta S over delta T would be 300 over 3, which is 100 kilometers an hour. Now, some of you are going to wonder, why did I write S? Don't get caught into thinking that S is speed there, because really velocity is the thing that's connected to the word speed. Okay, they're not exactly the same thing, but velocity here would be my speed. This is the change in distance, and we're using S for the change in distance. S stands for spatium, which is the Latin word for space or for distance, okay? So on average, over these 3 hours, Sam went 100 kilometers an hour. Now, does that mean Sam was always 100 kilometers an hour? No, right? Sometimes Sam was 95 kilometers an hour. Sometimes Sam was 105 kilometers an hour. Sometimes Sam got a heavy foot and was 140 kilometers an hour and then saw a cop. So he slammed on the brakes and went down to 70 kilometers an hour as he waved to the cop. You know what I mean though, right? So Sam's rate was probably constantly changing throughout. So we were able to determine Sam's, oh, I didn't answer the question there. Nope, there you go. I should hide my head one more time as well. Sam's average velocity is 100 kilometers an hour. That was the question I just asked you. All right, good stuff. We were able to determine Sam's average velocity over a time interval of 3 hours, but how do we determine his velocity at a given instant in time rather than an interval in time? And that's what I want us to look at right now. So we're going to switch equations here. We're going to have a displacement function. So S is going to equal this equation, f of t equals 5t squared, where t is the time in seconds. Okay, again, I'll just pop my head off for a sec so you can see the full question in case you don't have a book wherever you are. Complete the following table of values. So, hey, we're just plugging in 1 for t, 1 squared is t, so that's 5. Plugging in 2, 2 squared is 4, that's 20. Plugging in 3, 3 squared is 9, times 5 is 45, right? So we get 5, 20, 45, and 80. Okay, now I want you to complete the following statement to determine the average velocity from t equals 1 to t equals 4. Well, if I want the average velocity from t equals 1 to t equals 4, I'm going to use 1 and I'm going to use 4. That's 2 points. I can figure out the average by taking the slope. So I'm going to go 80 minus 5 over 4 minus 1. Okay, 80 minus 5 over 4 minus 1. Now, to be a little bit succinct in what I'm going to say, 80 is really f of 4, right? F of 4 means the y value at 4. So I'm going to write it like this. F of 4 minus f of 1 over 4 minus 1. So that's saying the y value of 4 minus the y value at 1 over 4 minus 1. So that gives me my 80 minus 5 over 3 equals 75 over 3, which is 25 meters per second. Friends, don't forget, most of you, this is not your first rodeo with me. You've gone through other courses with me. The power of a video that you're watching is two things. Number one, if you can't sleep, you can turn me on and I can help you fall asleep because I'll bore you. Number two, pause me, rewind me, okay? Make sure you're using these videos the best way for you, okay? Don't just watch me show an answer. You should always be pausing me, trying to get those answers yourself, and then looking at mine and comparing notes, okay? Okay, so from 1 to 4, we got 25 meters per second. Now, so that's from 1 to 4. What if I wanted to go from 1 to 3 instead? Okay, let's try that now. Now we're gonna go from 1 to 3. So I'm gonna go f of 3 minus f of 1 over 3 minus 1. Okay, so f of 3 minus f of 1 over 3 minus 1. Do all my math there, that's gonna give me 20 meters per second. Okay, what if I wanted to go, some of you are catching on to what I'm doing. What if I wanted to go from 1 to 2? Like that, okay? Well, if I wanted to do that, I would end up with f of 2 minus f of 1 over 2 minus 1. And that ends up being 15 meters per second, okay? What I want you to notice here is I'm approaching 1. I started going from 1 to 4, then I went from 1 to 3. Sorry, I should have kept that one there. I started going from 1 to 4, then I went 1 to 3, then I went 1 to 2. Okay, so what I'm doing is I'm taking this point here and I'm approaching 1. My answers then are going to be approaching the slope of the tangent line at 1. Okay, that's the big take-home message, and I'm going to show you this in a couple different ways, so don't stress out if you're sitting there thinking, what? It'll come, okay? Okay. With these last 3 questions, what were we doing? I just answered that. We were approaching 1. Okay, so gotta hide myself for a sec. The instantaneous velocity is a little trickier to simply calculate, as the change in the independent variable would be 0 and the division of 0 is undefined. So what we do instead is we approach it, okay? Now, I'm actually just gonna draw you a quick little picture here before we move on, just so that you can kind of get an idea of what I'm doing. So if I did this, whoops, okay, and I said, okay, here is a graph, and I want to figure out the instantaneous velocity right there, okay? So essentially, I want the slope of the tangent line right there. Okay, but how do I do that? Well, I could start by saying, okay, let's put a point here and let's get the slope of that tangent line. And then let's put a point here, let's get a little closer and get the slope of that secant line. Sorry, I said tangent line back a couple seconds ago. I should have said secant. I know you're all yelling at me anyway, because you caught that right away, right? And then let's get a little closer and let's maybe get to here and let's see the slope of that secant line. And what I want you to notice is as I move that original pink point closer and closer and closer to my orange point, the line that I'm drawing is getting closer and closer and closer to actually what that tangent line is. Okay, so I can look at the number, the slope that, or the number that the slope is approaching, and that's going to give me a really good estimate at the moment as to what the slope of that tangent line would be. Okay, and it's the slope of the tangent line that is the instantaneous rate of change for that moment. Okay, so by the way, that's called a limit. It's not about being at a specific point, but it's rather about heading towards that point. It's about what's happening to our outputs as we approach a particular input. Okay, think of it this way. We are asking for the rate of change at a point, but we've never done that. We've never just used one point. We've only ever found the rate of change using 2 points, which is the slope formula. Okay, so I'm going to walk you through this visual as well. I'm going to hide myself for 1 sec. The following graph is a partial graph of f of x equals -1/2 x squared minus x plus 12. Okay, let's think about drawing the tangent line for the following graph at x equals -4. The slope of the tangent line would represent the rate of change at x equals -4. Okay, I've said that a couple times now, so hopefully that's feeling okay. But I can't do that. I need 2 points in order to do that. Okay, so let's start with 2 points. We're going to start with x equals -4 and x equals -2. So when x equals -4, I'm at 8. And when x equals -2, I'm at 12. Okay, so I can just plug that stuff right into the formula. 12 minus 8 over -2 plus 4. I'm going to get a slope of 2. That is what that pink line is going to look like right there. Okay. It's close to what the tangent line would be, but you can see even before I moved my hands, right? It should be a little steeper. Okay. So let's get closer. Well, if I want to get closer, I just pick a point that's closer to -4. So, okay, that's close to what I want, but it's not totally accurate. What if I move the second point closer to the point I actually want? Now we say, what if I approached the point I actually want? Let's use the points x equals -4 and x equals -3. Okay, so the first time I use -2, now I'm using -3. I'm getting closer and closer to -4. So at -3, I am, I think, about 10.5. How do I know that? I'm just going to plug it in right here. Okay. Yeah, -3 and 10.5. Okay, so if I plug that into the slope formula, now I'm getting a slope of 2.5. Okay. 2.5. Now I'm going to change the slides here, and I'm going to switch from the pink secant line, which was using -2, 12. And I'm going to change to an orange secant line, which is going to be using the point -3, 10.5. You ready? Pay attention. Notice that it got a little steeper. Okay, I'm getting a better estimate of where I am at -4. Okay, super. I'm getting there, but can I get closer? And the answer is, of course I can. I just get closer to -4, right? So how about we try 3.9, or how about, sorry, -3.9, or how about we try -3.999 or -3.9999, right? Okay, so what we're going to do is we're going to play around with this table. And you're obviously going to want to pause me, and you're going to try and fill this table in yourself. Okay, but what we figured out right now is that a equals -2. My slope was 2. When a is -3, my slope was 2.5. I want you to plug in -3.5, -3.9, -3.99, and -3.999. I'm obviously not going to give you time to do that on a video. You're going to pause me and do it yourself. Okay, and these are your answers. And what I want you to notice is, oh, look at that. I'm approaching a slope of 3. My slope goes from 2.75 to 2.95 to 2.995 to 2.99995. I'm approaching a slope of 3 here. So I'm thinking to myself, hey, a really good estimate of this slope for the tangent line at -4 will be 3. Okay. So as I approach x equals -4, we can see that the slope of the tangent line becomes 3. This tells us that the instantaneous rate of change at x equals -4 is 3. And now the blue line that I've drawn is the actual tangent line there. Okay, so the rate of change of the curve at that point is 3. This is so fun, but don't get overwhelmed, right? There's nothing I'm doing here that we didn't really do in grade 10. So we got this. We are going to master calculus. Okay, so where do I use this in real life? Well, here's a couple of examples for you. Okay, and we're going to try another example. This is kind of a AP style question. One of the things with your AP exam that I want you to be aware of is they will often give you this big long context like this, and then they will ask you like a bunch of questions based on the context that will pull things from everything you've done all year. Okay, so I throw this question at you today. I might throw this question at you in a month's time, but I ask you a completely different question with it, right? That's kind of the cool thing. Okay, I'm going to hide myself for 1 sec. The spread of a rumor is modeled by the function r of t equals 2500 over 1 plus 50 e to the negative 0.25t, where r of t is the number of people that have heard the rumor, and t is the number of days since the rumor started for 0 to 30 for my values of t. Okay, rumors only last about 30 days. Then it's old school. There's a new rumor that started. If there's a rumor going around about you, just wait 30 days and everything will be better. Hopefully. The graph of the function r and the line tangent to r at t equals 4 is shown. Find an estimate of the instantaneous rate of change of r at t equals 4. The y scale is going up by 25. Now, a couple of things. First of all, I want you to see that this says find an estimate. Okay, we're not looking for it exactly yet. We will figure it out exactly in a few lessons from now, but right now we're just trying to play with the concept of estimating what that might be. Okay, so this is the picture that you have. And so there's two different ways I could do this. Number one, I could say, okay, well, I was given the tangent line. I could just try and figure out 2 points on the tangent line and use the slope formula, y2 minus y1 over x2 minus x1. Okay, so I grabbed a couple of points that I think are there. 125 looks good, 125 looks good. Plug that into the slope formula down below here, and I'm going to get around 33. Okay, around 33. Okay, so that's one way. I was given the equation of the actual function, that black curve there, right? That is the rate, or that is the growth model equation of this rumor. I'm looking for the tangent line right here, right? So what I could do is pick a point on the line, the actual line, not the tangent line, maybe right here, that's super close, and pick this point that's super close and calculate that slope. That's actually going to give me a better estimation of what the slope of that pink tangent line is than randomly guessing down here that this is the point 125. Okay, so let's do that. So this time I'm going to say use the equation to approach t equals 4. So again, I've given you one of these fun tables that you get to work with. We're going to go f of a. We're going to change a here, right? So right now I'm approaching 4 from the right because I'm going 4.1, 4.01, 4.001. So I'm approaching 4 from the right. Okay. So you go ahead and fill that in. Pause me. And these are your answers that you got. And then we would want to be comfortable to say, oh, look, I'm going to land around through 30.6 here, 30.6. So actually 30.6 is going to be a much better estimation of the instantaneous rate of change at 4, at t equals 4, than the 33 that I originally had. Okay. Okay. Take a look at this then. Which of the following would give the best estimate for the instantaneous rate of change of r at t equals 4? So would we do r of 4, the slope that goes from 1 x or t equals 1 to t equals 4, the slope that goes from t equals 4 to t equals 8, or the slope that goes from 3.8 to 4.2? Now, right away, I would want you to look at this guy and say, okay, that's not what I'm looking for. That's r of 4. That is the point on the graph when t equals 4, but that has nothing to do with the slope, okay? So to get the slope, I need those 2 points. So all of these guys actually are valid ways of getting an estimate. You have to pay attention to the fact that it says, what is the best way? And the best way is to have your points as close to the point you want as possible. So if I want t equals 4, having this 3.8 and 4.2, I'm just on one side of 4 and I'm just on the other side of 4. Whereas A and B, that's actually a span of like 4 points away, right? That's going to give me an estimate, but it's not going to give me as good an estimate. So D is actually the way to go there. Okay. You want to be as close to the point in question as possible. All right, good. So the displacement in meters of an object, I'm just going to hide myself for one more sec, is given by S equals t squared plus 2t, where t is the time in seconds. Determine the average velocity from t equals 3 to t equals 5. Okay, well, that means I'm going to find the y value when t is 5, the y value when t is 3, plug it into the formula. Okay. Okay, so my average velocity ends up being 10 meters per second. 10 meters per second. Okay. No worries there. All right, now it says estimate the instantaneous velocity at 3 seconds by using t equals 2.9 and t equals 3.1. Well, I'm doing the same thing, right? I'm just going to find the y value at 2.9 and the y value at 3.1, plug them into the slope formula. Okay, nothing's really changed, except the 2 points I'm using are really, really close to 3. So that's going to give me a good estimation of the instantaneous velocity at t equals 3. Okay, so when I do the math on that, I end up with 8 meters per second. Okay, we got this. All right, how could I get a more accurate result? Well, essentially, go closer, right? The closer you can get to your target, the more accurate your results will be. All right. I'll hide myself so you can see this question. A spherical balloon is being inflated. Determine the rate of change of the surface area with respect to the radius when the radius is 8 centimeters. And we gently reminded you that surface area is 4 pi r squared. Okay, so I have 8 centimeters as my target. So I'm going to figure out maybe 7.9 and 8.1. So here's my 7.9 and here's my 8.1, and I'm going to plug those into the slope formula. Okay, so y2 minus y1, right? I'm just plugging in those x values to get out my y values. Okay, it's still just the slope formula. y2 minus y1 over x2 minus x1, I end up with 20 pi times 3.2, which is going to give me 64 pi. And then my units will be whatever my y units were over whatever my x units were. So that's centimeters squared over centimeters. Don't think that a centimeter divides out there because it's talking about the units of 2 different items, right? One is the rate, or one is the unit for surface area, and one is the unit for the radius. So better to say centimeters squared over centimeters. Okay, awesome. So here's your homework. If you're one of my kids at school, make sure you're trying it, make sure you're checking your answers, and make sure you're asking me lots of questions. Congratulations on finishing your first note. We have an exciting journey ahead of us. Okay. All right. You guys got this. Talk to you soon.